So can we formalize this definition in any way? So we can make progress on formalizing this idea with two key observations. The first one is, I think, probably a little bit subtle, which is that given composable arrows F and G in my putative infinity category structure, it may not actually make good sense to speak of the composite of those two things, because in fact, any arrow that's homotopic to that putative composite has equal right to that crown. Really, we're not interested in the specific identity of that composite. We're interested in the fact that there is some homotopy. I mean, there's a bunch of different maps that have the, that we might reasonably expect to think of as the composite. And all of those maps are going to be homotopic. In fact, more specifically, there's a subspace of all of those possible composites, and that subspace should be what homotopy theorists call contractible. And I think Emily probably talked about the importance of contractibility in this kind of thing in a talk that she gave at the Topos Institute last year. So the first thing is, we're not necessarily going to think of there being a specified composite. We're just going to have some kind of way of recognizing those things that are composites of other things. And then the second thing that we might observe is that higher associativity laws arise from the algebraic structure of higher simplices. So for instance, a two-simplex tells us something, so a two-dimensional triangle tells us something about the structure, tells us something about how things compose. So if I have a triangle like this in my space, so the idea is to interpret this as saying, well, I've got a path in my space F, I've got a path in my space G, and I've got another path in my space that I've chosen to call G composed with F. And there's somehow a nice homotopy, there's a nice sort of piece of continuous space that witnesses that these two paths have been composed together to give me a third path, G composed with F. And as I say, I mean, there may be many, I mean, I'm using the notation G composed with F here just because I need to use some notation, but there may be many different candidates for this G composed with F. Anything is going to be a candidate if there is some nice piece of space that relates F and G to that third thing at the bottom in the form of a two-simplex. So then we can look and say, well, what does the three-simplex tell us? And when we start drawing that situation, so we take a three-simplex, so a three-dimensional triangle, and we kind of flatten it out. So we take pairs of its faces and we draw two of those faces on the left and two of those faces on the right. So the idea is, think of this as sort of we've decomposed the three-simplex into two pieces. We can reassemble it by folding these two pieces along these edges here and then gluing them back together around here. You'll notice that those are labeled F, G, and H, and this is F, G, and H. So I'm actually gluing those together. And those four faces tell me that, for instance, this map here is a composite of these two things. And this face here is telling me that this map here is a composite of these two things, and so forth. And in fact, to make this a well-defined sort of simplex, I need to make sure that this edge along the bottom here that really represents, I guess this says, take F and G and compose them together to get this thing, G composed with F, and then compose that with H to get this thing along here. This thing here says, take G and H first and compose them to get H composed with G, and then compose F on the front to give this. And to make this the boundary of a well-defined simplex, I really need to make sure that this thing is the same as that thing. I'm not really being very precise because I said to you that I shouldn't ask for two things to be the same, but the idea is that this rule here tells me something about associativity. It's the thing on the left, which is two of the faces of the three simplex tell me about the composite of these three things, F, G, and H, one way around. The faces on the right tell me about their composite the other way around, and the fact that they fit together into a simplex tells me two things. It first of all tells me that the composites both way around are related, and it also tells me that there's some kind of homotopy in the middle of that three simplex that relates this piece of witnessing data and this piece of witnessing data to those two there. So that's the sense in which associativity is a 3-simplex. And it turns out that the MacLane pentagon is a 4-simplex, and I'm not going to go through the details of where that comes from. But maybe if you read, I guess Ross Street wrote a paper called The Algebra of Oriented Simplices in the 1980s, and he has some really nice pictures and explains how it is that we extract the MacLane pentagon from the 4-simplex in this way. And in fact, what we discovered over very many years, I guess since the 1960s, is that the higher coherences that these things must satisfy naturally form higher simplices. It's one way of seeing them as higher simplices. So various methods have been explored to directly formalize our intuitive model, the one where we had spaces and so forth, using those last two ideas. And these give rise to a number of formal models then. So we have an intuitive model. This is kind of what we're looking for. And various people have come up with formal models to try and make that more precise. And a number of things that you'll find in the literature include things called complete Siegel spaces and Siegel categories and Tam-Samani categories and so forth. These are all models that were intended to, I guess, specifically, give a sort of close model of the intuition that we had, a structure with objects and spaces of maps between them. But we'll actually look at a slightly different kind of model for what we do here, which is a thing called a quasi-category. And I'll look at this really briefly because I noticed that I'm already running well behind time. So a quasi-category, which is maybe one of the most popular models of infinity category, is essentially a thing called a simplicial set. So a simplicial set isn't something we're going to define here, but essentially it's a topological, or it's a combinatorial model of a topological space that's built by gluing together simplices. So it's built by taking points and gluing lines between them, and then gluing triangles between those, and then gluing tetrahedra between those, and then gluing higher and higher simplices on to build up my space. And this is really a combinatorial model of that. And it's not really particularly important how that model works, except to say that inside that model, we can identify things that correspond to the simplices at each dimension of this structure. And the combinatorial structure tells us how those simplices are related one dimension to the next. Now, the way that so we take a simplicial set and we say that a quasi-category is something which is a simplicial set that admits things called fillers for inner horns. And rather than defining for you precisely what that means, I'll just show you the first couple of examples. So a filler for, I guess, a 2-dimensional or 1-dimensional horn in this case. So the horn looks like, in my simplicial set, looks like just a pair of edges. So the 1-dimensional structure of this simplicial set, they're just directed edges. So I take an edge called F and I take an edge called G, and that thing together is called a horn. And the reason it's called a horn is it kind of looks like this picture here. I've got, I guess this is the point that I blow into the horn, and this is the bell where the sound comes out here. It's a simplex where I've thrown away the top dimensional data of the simplex, and I've also thrown away one of the other faces. So I've got no simplex filling in here, and I haven't got this face here, but these are the remaining 2 faces. So I've got F and G. That's the input data to some kind of operation. I want to compose them together. And the way I compose them together is I do a thing called filling. So somewhere inside my combinatorial simplicial set, I posit that there is a 2-simplex starting with F and G, which gives me both a K, which I think of as the composite of F and G, and gives me a 2-dimensional simplex here, which we think of as the homotopy. That homotopy is a piece of data that states K should be regarded as a composite of G and F. Now, I'm not making any assumption that that's unique at all. So there may be many simplices that can fill this in this way. So there may be many ways or many different simplices that have as their top 2 edges F and G, but which might have a different K and a different twiddles filling it in. We're not asking for uniqueness at all. We're just asking that such a thing exists. So a composite of F and G exists, but there may be many such things. And then at the next level, at the two-dimensional level, this is what a horn looks like at dimension 2. So again, a horn looks like a simplex where I've thrown away the top dimensional information. In this case, that's the three-dimensional information. And then I've also thrown away one of the other faces. So in this case, I've got this thing here has all of the information that I might normally have in a 3 simplex, except that it's missing this face here, and it's missing the top dimensional information here. It can't have that top dimensional information there, because for that to be there, I'd need to have that in here. And the filling process says that somewhere in this simplicial space, there is actually a genuine, in this case, 3 simplex that has all of this data as various of its faces, but adds for me the extra data of something here and a homotopy in here. So what this something here does is it witnesses that the composite, or it witnesses that L can be regarded as some kind of composite of H and K. And so again, what this filling process says is essentially, if I start with some composite of F and G on this side, call it K, and I start with some composite M of G and H, and then another composite L of F and M, then on the other side, I can find a thing in here that witnesses that I can regard L also as a composite of K and H. Okay. So one of the reasons for explaining this at this point is just to explain that, well, this is already far too complicated for, without some extra technology, trying to do category theory with this kind of structure is going to be a little bit confronting.